We are here at the LiFi Research and Development Center at the University of Cambridge. In this lab, we built wireless communication systems using the optical spectrum, which is light from ultraviolet light all the way down to infrared light, including visible light. The entire spectrum of light communications is about 3,000 times larger than the entire radio spectrum. This is one of the biggest motivations for us to use optical spectrum to build wireless systems. The optical spectrum has also bigger advantages in terms of security because light doesn't go through walls, so you build much more secure systems with it. And also it can be applied for a whole range of applications indoors to build tens of gigabit per second wireless indoor systems like your Wi-Fi, but instead of radio, we use light. But it also can be used underwater to build underwater systems. It can be used to connect aerial platforms such as drones and high altitude platforms, but also it can be used to connect ground station with satellites and allow satellites to be connected as well with light. There's a huge amount of spectrum available and a huge amount of use cases that we are targeting with our fundamental research on new devices, on new systems, and then bringing everything together into new use cases. The technology also, because it uses light, has advantages in terms of lower energy consumption. So we build net zero wireless communication systems in addition to lower costs because we use off-the-shelf devices in many cases, allowing us to build scalable low-cost systems.
Our experiment focuses on wavelength division multiplexed LiFi system. In this system, we are using multiple channels, and then each channel is almost sending around 10 gigabit data rate. If we have 10 channels, we hope that we get aggregated data rate of around 100 gigabit per second. The current Wi-Fi system are suffering from the limited available RF spectrum, and the LiFi can take advantage of its license-free spectrum, high speed, and also the high security.
The idea here in this experiment that we use high bandwidth, high brightness laser diodes to produce such a high data rate. So here we are using a surface-mounted device which contain two laser diode sources, and these two laser diodes are mounted in the edges of a surface-mounted packages. The orientation of the two laser diodes are configured so that the emitted light incident to the phosphor reflector in the center of the package. Now, the first laser diode is emitting a blue light at 450 nanometer. And this blue light, when incident to the phosphor reflector, part of this light is converted into a yellow light. Then, the combination from the blue and yellow light forms the white emission for illumination purposes. The second laser diode uses a different material so that it can emit different wavelengths. In this experiment, we use 10 different wavelengths so that we can build a 10 parallel LiFi communication channels with wavelength division multiplexing to achieve 100 gigabit per second. Currently, we're enabling 80 channels, and as you can see here, we can achieve around 80 gigabit per second. The demand for high data rate is exponentially increasing. So the existing RF wireless communication or radio frequency communication technologies will face some challenges related to interference, high cognitions, and limited bandwidth. LiFi presents here alternative solution or complementary solution to radio frequency technologies, which can achieve ultra-high data rate using existing infrastructures. For example, when we utilize the existing light in homes or the existing light infrastructure in vehicles and traffic signals, we can use this existing light for both illumination and data communication, which is actually brilliant for this technology.